Hello everyone, welcome to another stream from Codes of Interest. Today we are going to look into Google Colab and see how the different backends it offers, CPU based, GPU or TPU, and how those affect the training speed of a simple Keras model. So I'll go ahead and create a new Python 3 notebook. And what I'll do is I'll first change the runtime to GPU. Hit save, and I will click connect here so that I am connected to the Google's runtime backend. Okay, now we are connected. You can see it's the Python 3 Google Compute Engine GPU backend. We get 12 GB of GPU memory with 358 GB of storage, and here you can see the directory structure as well. So let's go ahead and start creating our model. So I'll create the very simple MNIST model for handwritten character recognition. I'll use Keras and TensorFlow for this, and we'll use the Keras sequential model. Here we are importing all the necessary libraries we need. Let's go ahead and run it, and it's using the TensorFlow backend. Looking good. One important thing when you are using Google Colab is when you are using OpenCV, the cv2.show method does not cv2.imshow method does not work on these Jupyter notebooks, so instead you will have to use this thing. It's actually a patch provided by Google Colab itself, and they have their own cv2 imshow method that you can use to work within the Jupyter notebook itself. So I'll import that as well. Oh, and I almost forgot, need to give a name to this file. I'll name it MNIST speed test. You can name it whatever you like, and I'll save the file just in case. Okay, now we have imported all the libraries we need. Let's start building the model. I'll add a function here that will actually build the network structure that we need. And it's a very simple sequential model, couple of convolutional layers, and final dense layer that you use to predict the digit that's from the MNIST dataset. We'll also add another utility function so that we can see the training history graph. We'll be using matplotlib to display the graph. So I'll go ahead and run these code snippets. And let's start building our model. First we'll load the MNIST dataset. As you can see, the first time you load it in your code, it will download the dataset and place it in your Keras home directory. We'll do the necessary pre-processing of the data. That includes reshaping the data to fit Keras and TensorFlow, rescaling the data so that all the pixel values are between 0 and 1, and then encoding the labels so that those categorical values are mapped to a numeric vector. Now we'll use the method that we defined previously and create the model. So the width and height of our input images are 28 by 28 pixels, and since they are grayscale images, the depth is 1 and now classes is 10. We don't have any weights at the moment since we haven't trained the model yet, so we'll set the weights path to none. Next we'll compile the model. It's a categorization problem, so we'll use the categorical cross entropy. We'll be using the SGD optimizer as well. So let's go ahead and run it. There are a few warnings, those are normal. Now it's time to actually run the training. We'll set the batch size to 128 and run for 20 epochs. Let's see how it goes. So the training appears to be going very smoothly and sufficiently fast. So that's around 3 seconds per epoch. We'll see how this compares to other backends. Remember, we are running on the GPU backend right now, so the training is now over. Let's run an evaluation on the dataset and see. So it's 98.82% accuracy with a 0.03 loss. Let's see the training history as well. History looks good. We don't see any sort of overfitting. We'll now save the model weights to a file so we can reuse them later on, and I'm saving them to this content path, which is here. So if you refresh, you can see the file pop up here. Now our training is complete, so let's run a small evaluation of our own and see how it performs. So we'll basically take some random set of images from the the testing dataset and run predictions on those and see how it performs. So again, as I said, we can't use cv2.im show here, so I'm going to use the custom option provided by Google. Just replace this, and there's no title here, and we don't need the cv2.wait key. So okay, looks good. Let's run and see. Okay, let's see. So predicted versus actual, I think it got everything correct. Looks like it. Let's try a rerun and see whether we get different results. No, still looks good. So that's the Lenet MNIST model being run. So in order to see how much time it takes for training, let's add few lines of code to calculate the time. We'll need some time calculations. We'll take the start time here. And the end time after the model is trained. And we'll take the difference of those two times as the time taken for the training. Let's clear these output first, and let's try rerunning it. So that's looks like the total training time is just under 1 minute, so that's 55 seconds. Now let's see what happens if we switch to a different backend. We'll switch the runtime. We are currently on the GPU accelerator, or the GPU backend. Let's see what happens if we switch to CPU. You can see here that it's connecting to the new backend. Connected, and since we switched the backend, we need to rerun all the code because we lost the state of the machine. Okay, let's run the training this time on CPU. Okay, from the start we can see that it's very slow compared to GPU. We have an ETA of 1 minute and 30 seconds per epoch. If you remember, last time we did the entire training, entire 20 epochs in less than 1 minute, so you can see that running on CPU is taking longer. So it took 113 seconds for a single epoch. So if you remember, last time on GPU it took only 3 seconds per epoch, and the entire training completed within 55 seconds. So this is obviously going to take much longer, so I'm not going to run the whole thing. I'll just stop it here. And the last thing we need to test is how it's going to behave on a TPU. Now TPU is Google's proprietary tensor processing unit. It's supposed to be specialized hardware that deep learning models can be run very quickly, but the thing is you need to optimize your model to run on a TPU to get the full benefit of it. Otherwise it's not going to give you much of a speed increase. So we'll actually going to see how it behaves with this simple model which we haven't optimized to run on a TPU. So I'll go ahead and switch the runtime, and it's connecting to the new runtime here. Okay, we have the TPU backend right now. Let's clear these outputs. And see how it behaves. Okay, let's run the training once again. And you can see that the ETA is even higher than CPU at this point, although it seems to be reducing as it goes. So it's obvious now that even though this is a very simple model, it's not taking any advantage from having a TPU. You need to optimize your models to utilize TPUs if you are ever going to use them. Until then, I believe GPU is your best option. So that on the GPU backend it works really well and about 10 times faster than CPU and TPU. So although we get access to free TPUs from Google Colab project, we are not going to be able to utilize them unless we are going to spend time and optimizing our models to work with TPUs. But still, we can use the GPU backends. It's, I believe, Tesla GPU, NVIDIA Tesla GPU backend that Google is providing, which is really good since it is given to us free of charge. So that's a good option for every one of us to run our deep learning experiments on a GPU if you haven't got a GPU deep learning machine with you at home. So I think we are just about completing a single leap of the training, and again it's 115 seconds, and you can see that this is not going to come even close to the speed of the GPU. So that's it for today. Hope you learned something today. We'll see you on the next live stream.